3,161 block placement queries. Key idea: keep track of obstacle positions and answer each placement query by computing the largest continuous free interval inside 0x. If that interval is greater than or equal to SZ, the answer is true. Coordinate compression: store all possible obstacle coordinates, type 1 queries, and compress them into an array coords. This lets us build a segment tree only over actual obstacle positions instead of the whole number line. Segment tree state per node: each node stores 3 values: leftVal, smallest occupied coordinate in the node, or -1 if none; rightVal, largest occupied coordinate in the node, or -1 if none; maxGap, largest gap between consecutive occupied coordinates inside the node. These 3 values are enough to compute the largest free continuous interval when we combine nodes. Merge logic: why it works when merging 2 child nodes A and B. If one side has no obstacles, return the other. Otherwise, the combined maxGap is the maximum of A maxGap, B maxGap, and the gap between the boundary obstacles B leftVal, A rightVal. This preserves the largest internal gap across the combined range. Answering a type 2 query for range 0x1. Find the last compressed index IDX with coords IDX is less than or equal to x2. Query the segment tree on 0 IDX to get first, last, max between. 3. The largest free continuous interval inside 0x is max, first 0, max between, x last. 4. Return true if that value is greater than or equal to SZ, otherwise false. If there are no obstacles is less than or equal to x, the free interval is x. Complexity and why it's fast preprocessing: compress coordinates in OQ log Q. Updates and queries: each is O log M, where M is number of distinct obstacle positions. Memory is OM. This meets the constraints and is efficient for up to 1.5 times 10 to the power of 5 queries.